All right, good evening guys. We'll get started. Is my mic working? Okay, we're all set. So, last class we introduced the idea of propositions and we talked about what a proposition means and how to define them and how you can connect multiple propositions to make bigger and bigger propositions. So today I want to talk about where these really come from in the first place, how do we get to them, and how do we get away from them. So what that means is, really, how do we translate from English into logic and back? How do we go from these sentences in logic to English? This has two benefits. The first is that you're going to need to perform these operations if you want a computer to reason, for starters. And the second thing is if you really understand how to do this, then I know for sure that you know how the connectives work. So this is a good way for me to test your knowledge of how to do this stuff. So the topic of today's class will almost completely be translating sentences. And once we have that, we'll start talking about things we can do once we have those sentences translated. But even once we're onto that topic, we'll still need to know how that translation works, because many questions you'll get will have something to do with translation, right? That might just be the first step of the question, but you'll need to know how to do it. So we'll see a bunch of examples. The first thing I'm going to do is give you a sentence in logic and then ask what it means in English. Okay, that's where we'll start. So let's define a few propositions. So let's let A be the proposition: the computer lab uses Linux. And B be the proposition: a hacker breaks into the computer. And we'll have one more proposition, and that is C, which will denote the data on the computer is lost. Okay, these are three propositions, and I'd like to know what some things in logic are in English given these definitions. So the first one I'd like to know is, what is A implies not B, and not B implies not C? What is that saying in English? Does anyone have any ideas? Yeah?
Because the computer lab uses Linux, a hacker is unable to break into the computer. And as a side effect of that, because the hacker did not break into the computer, no data on the computer is lost.
Okay, so you're on the right track. The thing that worries me a bit is the use of the word because.
Okay.
Because is one of these things that's like since, and in casual language it sort of feels like an implication, but in logic it's really just a conjunction. So how would we correct that? Yeah? 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 Exactly. So the sentence is saying, if the computer lab uses Linux, then a hacker will not break into the computer. And if a hacker doesn't break into the computer, then the data on the computer won't be lost. Right? There's sort of two parts to this. There's this first part on the left and this second part on the right. Sometimes when you're translating these things, it helps to break them down into these parts. So this sentence would be, if the computer in the lab, or the computer lab uses Linux, then a hacker will not break into it. And if the hacker doesn't break, or if a hacker does not break into the computer, then the data on the computer won't be lost. Now you might notice a slight shift in tense sometimes. That doesn't matter for what we're doing. You should change the tense so that the sentence sounds as natural as possible. Question?
If I use the word cannot rather than will not, would that mean something else? Or
Yeah, so technically, yes, but that's not what the question is about. So I do sort of change them around so it sounds the most natural. That's not what we're going to be examining, the difference between will versus can, when we ask these questions on tests or assignments. Anything that's correct will be fine, right? The critical thing is whether there's a not or what the connective is, not so much what the tense is or things like that. Question?
If I were to say something like, if and only if the computer log uses Linux, then the hacker will not break into the computer.
Right, so what you're doing is you are deriving facts from the proposition that's being given to you. That's something we'll address later. For now, translate the exact sentence you're given. Yeah?
it says the computer lab uses Linux, and it says the symbol in between the two sentences, isn't it the union symbol? Like the,
This symbol here?
yeah, isn't that and?
Yeah, that's and that's this and right here.
Okay, so that implies that. Okay.
Yeah. Other questions? All right, so let's do another example. Let's do not A or not B. And notice that the first negation is outside of the parentheses. It applies to the whole thing. What does this mean? Any ideas? Yeah? Yeah, so you can do things to just the logic. Let's go to English without doing anything first. Yeah?
It is not the case that the computer lab uses Linux or the hacker doesn't break into the computer.
Yeah, so that's good. Does that sound kind of ambiguous or awkward to people? There's nothing wrong with your answer. This is something I'm saying about English, not about your answer. In the back?
The computer does not use Linux, and a hacker breaks into the computer.
Right, so this is again something you're doing to the sentence. Why are you doing that to the sentence?
Because when you have a negation in front, it changes the or to an and.
Right, but why would you want to change the sentence? We'll see that is in fact the case later. Why wouldn't you translate this one directly, whereas the first one we would translate directly? Yeah? Yeah?
Because we kind of expand the negation, and that kind of flips it.
Yeah, in English, it's very unnatural to use negation to apply to a whole bunch of things. If you remember back to the end of last class when I was talking about the precedence of these operators, I said that negation applies to the smallest complete thing after the negation. And that's a rule that we're actually pretty comfortable with in English, whether we realize it or not. And so to have this negation on the left applying to so much, even though it's not ambiguous in the logic because of the brackets, in English we don't have those brackets. So if you try to translate this directly, you would say, it is not the case that the computer in the lab uses Linux, or the hacker does not break into the computer. It's ambiguous where I'm putting the not when I say it, because I can't verbalize parentheses to you. Okay? So that tells you, well, I mean, let's translate this thing. I'll write that down. It is not the case that, well, to sort of give myself parentheses, I can use the English construct either. And then that kind of tells you that there's parentheses. So I could say it is not the case that either the computer in the lab uses Linux, or a hacker will not break into the computer. That's a little better, but still, this isn't a great sentence, right? If you were talking to someone and they said this sentence, you would probably have to stop for a second and think about what it means. So this is awkward. And we'll talk more about that later tonight or next class. You can do things to these sentences in logic to change them in systematic ways, just like you'd rearrange a formula. Question?
What is the point of parentheses?
So if you didn't have the parentheses, you would have not A or not B. And that might mean something else. In this particular case, it probably does mean something else. Right? This would be saying either the computer in the lab doesn't use Linux or a hacker will not break into it. Right? That's different from having the either, although I agree that it's still ambiguous. The difference will be clearer once we translate it another way. Yeah?
Does a negation always change an or to an?
So we'll talk about that later. When you have a negation outside of a bracket and inside you have an or an and, it flips it to the other one. But it also does things to either of the conjuncts or disjuncts, either of the things being anded or ored. Other questions? Okay, let's see another example. So I'll just say this is not equal to that. Another example would be C, if and only if, not A and B. Let me just rewrite this so it's clear. How would we translate that? I'll show you the, it's A is the computer lab uses Linux, B is a hacker breaks into the computer, and C is the data on the computer is lost. How do we translate this? Yeah?
Only if the computer lab does not use Linux and a hacker breaks into the computer, the data on the computer is lost.
So it's not only if is a single direction implication. We want if and only if. That's the bi-directional version. Yeah?
If and only if the data on the computer is lost, since the computer does not use Linux and the hacker does not break into the computer.
Yeah, so you can say it that way. Another way to say it would be the data on the computer is lost if and only if the computer in the lab does not use Linux and a hacker breaks into it. You could put the if and only if in the middle too. That's what I tend to do, but you can do it either way. So let's write that down. The data on the computer is lost if and only if whoops, I did the abbreviation and the full version. If and only if the computer in the lab does not use Linux and a hacker breaks into it. All right? All right. Let's start doing a few translations in the other direction now. All right. So I want to translate the sentence, if the hard drive crashes, then the data is lost. How would I translate this sentence from English into logic? Yes?
Assuming that hard drive crashing is D, then D implies C.
Okay, so in this case you're using C from the previous one, that's fine. So I'm just going to define brand new ones. Let's let H be the hard drive crashes and D be the data is lost. Well, then this means that the proposition is H implies D. Now what you did when you were answering that was very, very important, and that is you told me what the propositions meant. You said let D be whatever, let H be whatever. If you just put H implies D, that is worth very few marks because you haven't answered the question. I could write down any symbols in any order I want and define it to be the answer. That doesn't mean it's useful. You have to say precisely what you mean, right? That's the trade-off you get for going to logic. Logic is very precise, it has very clear rules, but you have to say exactly what you mean. Okay? So when I ask you to do a translation, you always need to say what those variables are. All right. So as another example, let's say the infrared scanner detects motion only if the intruder is in the room or the scanner is defective. So how are we going to translate this? First thing you should do, figure out what the small propositions are. This is obviously a big compound proposition. Let's break it down into parts. So one of them is the infrared scanner detects motion. Another one is the intruder is in the room. And another one is the scanner is defective. Everyone agrees that those are the three parts of the sentence? All right. So let's give those names. I'm going to say, I don't know, M is the infrared scanner detects motion. I is the intruder is in the room. And D is the scanner is defective. Now at this point you might think back to last class and you say, well, John said you shouldn't include a negation in a proposition, and in some sense defective is the negation of effective. And that's true, but there's not really a good argument either way in this case. When I say don't include a negation, I really mean don't include the word not. Okay? Use your judgment on these ones. All right, so what's the translation of this? Yeah?
Open parentheses, I or B, close parentheses, therefore M.
So implies M. Okay. Any other thoughts? Yeah?
I implies M, parentheses, or D.
Like that?
Yeah.
Okay. Other thoughts? Yeah? Okay. Any other thoughts? Yeah? Okay. Other guesses? Yeah? Sorry, M, if and only if. Or D. Other thoughts? Yeah? M implies I, or M implies D. All right. Any other thoughts? Okay. So we have a couple of choices here. What's the main source of confusion on this one? Why do we have so many different answers for this, but we didn't before? Yeah? The or I wouldn't really consider to be ambiguous here, although I agree that it kind of can be. Is it clear what the sentence is probably trying to say here? Yeah, the only way that something's going to go wrong is if the intruder is in the room or the scanner is defective. Right? It's probably not giving some condition where the scanner detects motion and then happens to give you this other fact that the scanner is defective maybe. All right? So really what's probably causing trouble here is this only. Right? Because you think back to last lecture and you say, oh yeah, there's this thing where if it's only if, it also means something like that, but maybe the order matters. So let's go back and check our notes. We'll see, P only if Q is the same thing as P implies Q. It's the same thing as if P then Q. Okay, there's no shame in going back to your notes and looking things up. That's what they're there for. So now that we know that, we go back here and we say, okay, this is going to be an implication, and the infrared scanner detects motion is going to be the thing that's on the left. Right? So it's not going to be this answer, because M is on the right. All right, so that's better. What else do we know? Well, it doesn't feel like it's going to be the second answer because we feel like we want the M or D part to be together no matter where they are. Although I agree that the sentence is somewhat ambiguous, it seemed like most people agreed that the or bound very tightly here. So it seems like it's not going to be that answer. All right, moving along, we have an only if. We don't have an if and only if. So what's not going to happen is we're not going to have any biconditionals. So these things here are also not going to be the answers. And then the very last thing, well, we've got it down to two answers now. We've got this answer, M implies I or D, and M implies I or M implies D. Which of those is correct? Yeah, so the consensus seems to be the first one. Does anyone have any thoughts on the other one? Yeah. Yeah. Are they the same answer? Okay, so we all seem to agree that definitely what could happen is you could have two answers that are the same but written differently. Does everyone agree with that? Okay. And maybe you can't tell just by looking at the second answer if it is the same. Right? I haven't taught you how to do that yet. I will by the end of today. Does everyone see the need for some systematic way to decide if two compound propositions are the same? That seems reasonable, right? All right. So that's what we're going to do in a second. I want to do a few more examples of translation first before we jump into that. Any questions about how I eliminated some of these answers? Yeah?
Not about that, but you mentioned the last thing you said. Does everyone see it clear why?
Right. So the impression I'm getting from what you guys have told me is some of you think that this answer circled in green is exactly the same as this answer here. I'm not saying it is or it isn't. We'll figure that out soon enough. But when you're giving an answer to the question, you only give one answer. So it would be nice to know whether or not these two remaining answers that we haven't eliminated yet, it'd be nice to know if they're the same. So what we need to do then is have some systematic way of figuring out whether two propositions are the same proposition. So that's what we're going to do in a bit. There's a question there?
No, it's just that they are really, they are technically sort of the same, but very minutely they are different. As the second one is saying that it cannot, if it is one, then it cannot be the other. But the first one is, it can be one, but at the same time, just because the alarm is defective doesn't mean that there isn't an intruder.
Yeah, so there is this issue. It's not completely obvious at this stage until you get a lot of experience with these things whether or not they're the same. So I'd caution you against just trying to do some intuition about it right now because we don't have the tools to do it yet. Yeah?
I was just gonna say, like, it is the same
Right. So, so basically the operation you're trying to do is you're trying to distribute that implication over a disjunction, right? If you add 5 times and then in parentheses 2 plus 3, you could do 5 times 2 plus 5 times 3. It's a similar operation here, but we don't know if that's valid. That's valid for addition and multiplication. Is that valid for disjunction and implication? We'll find out. Yeah?
The question is just, is the top one not more accurate because it says M only if I or D? Like, that's literally what the sentence says.
Sure. So in that sense, it's completely 100% accurate. If it were the case, though, that the second thing on the bottom here was equal to it, that would be equally accurate. Although I agree, it's somewhat misleading to not keep the same structure of the sentence. But if they have the same meaning, that's fair game. And sometimes you will want to massage things a little bit before you translate. For example, this example here. This I would probably want to manipulate a little bit before translating. Other questions? Yeah.
The first, I mean, the one that's not circled, that M implies I, so that would say like the infrared scanner detects motion if like you're repeating yourself, like the intruder is in the room, or the infrared scanner detects motion.
Yep.
So that's kind of repetitive if you do that way.
Right, so if you translated that back in English, it may or may not be the same. We'll find out soon. If you translated that into English, it would be a different sentence if you did it literally. The hope is that it would have the same meaning. Okay, we don't care so much about repetitiveness. It's okay if it's repetitive as long as it's accurate. Other questions? Okay, this is good. You guys ask a lot of questions. I like that. That's important, and you should continue doing that throughout the term. All right, so we'll do one more example here before we get into talking about these equivalences. All right, so if the server is down, and the network connection is lost, then email is not available. But I can still play games. Sadly, that's not actually true anymore. All right, so I would like to translate this into logic. All right, so the first thing you do is you break this down into parts. So let's do that. What are the parts of this sentence? Which should be a proposition? Yeah? So if is part of a connective, so you don't want to include the connective. So you just say the server is down. What else? Yeah? Yeah, the network connection is lost. What else? Yeah? Yeah, exactly. Email is available. This is a case when I would not want to include the not because it's sitting right out there. What else? Yeah. Yeah, I can play games. Oops. All right, so let's go ahead and come up with some things for these. I'm going to use S to mean the server is down. I'm going to use N to mean the network connection is lost. Again, here you could use N to mean the network connection is stable, although I don't really see a strong argument for going either way with that one. We'll use E for email is available. And we'll use G for I can play games. We don't really need to include still there. That doesn't really that's not really required by the logic. So how would we translate this sentence? Yeah.
So, open parentheses, X and N, close parentheses, implies, open parentheses, not E and G.
Okay. Other thoughts? I'm sensing more agreement on this one, and that's good because that's the correct answer. All right. So, any questions about how translation works? These are the kinds of questions you will see, and I spent a significant amount of time on it. So that should tell you that you will probably see a translation question in either direction on the first assignment, which will be posted tomorrow, by the way. And you will almost certainly see some kind of translation question on the first test. Yeah? Capitals for the names of the variables? Yeah, that's fine. Typically, it's lowercase, just like it's typically lowercase in algebra, but it's not a rule. Yeah? Yeah, so again, it's a little bit ambiguous. In this case, it seems like the if, like the implication, is the biggest thing. It takes up the entire sentence, so that's why I would put it in the parentheses. Yeah? Yeah, so at that point, it's a question of which binds tighter, implication or conjunction. I don't remember, so always do this. Right? It's much easier just to put them in than to remember the rules. Other questions? Yeah?
How is the email available if you connect
So
them?
the email is available as just the name of the proposition. It's not E that's actually in the sentence.
Okay.
Other questions? Okay, so that's what I wanted to say about translation. Let's move on and start talking about truth tables. And talking about truth tables, it's what's going to lead up to deciding if those two implications, or those two compound propositions, were actually equivalent. So before we jump into that, I don't want to talk about comparing two propositions yet. For now, I'd like to talk about determining the truth value of a compound proposition. So if you think back to last class, when I was talking about the connectives for the different propositions, I gave a truth table for each one. And the way the truth table worked was I told you the truth value for P and Q, and then I gave you the truth value for P or Q, or P and Q, or P implies Q, or P if and only if Q, or P exclusive or Q, or whatever. A truth table also works not just for those simple compound propositions, but also more complex compound propositions that have a bunch of ands and ors and implies in them, right? If we have truth values for P, Q, and R, say, we might want to figure out what the truth value of some compound proposition involving those statements is. Okay? So that's what we use truth tables for. We need truth values of the propositions that make it up. Okay? And you might say to yourself, oh, I don't actually know the truth values of some of these things. Right? In the above example, I don't know if the server is down. I'm not sure. So what truth tables do is they present all possibilities to you. So we use truth tables truth tables to look at all possible combinations. Now, you might say, John, you said that if you couldn't determine whether or not a proposition was true, it's not really a proposition, right? That's like x plus y equals 2 isn't a proposition because I haven't said what x and y are. And you just said that maybe you don't know the truth values of p and q. Well, not knowing the truth values of p and q is different from them being unknowable, right? I don't know if the server is down, but I could walk over to the server room and check. So that still counts as a proposition even if I don't know its truth value. Whereas x plus y equals 2, there's no way I could know that truth value because x and y could be anything. Right? It's sort of a subtle distinction. All right, so let's talk about how to make a truth table. Well, we've already seen examples, but they were kind of simple. So you have one column for every proposition. So if you think back to the truth tables we saw, for the truth table for P and Q, we had a column for P and a column for Q. And once you do that, you then take the compound proposition and you break it into parts. All right. So that's how you come up with the columns. So each part of the compound proposition will be another column. And now you have one row for each truth value combination. All right. And then all you do is you fill in the table by working with the smaller parts first and building up to the whole proposition. And if that seems strange, hopefully it'll be clear when we do an example. So let's do an example. The example I want to do is P and Q implies not P or Q. So I want to do a truth table for this thing. So first I say to myself, what are the propositions here? Well, the propositions are P and Q. There's no other letters involved. So I have a column for P, and I have a column for Q. All right. And now I break the compound proposition up into parts. So what are the parts of this compound proposition? Well, the whole thing is this. And I want to break that into parts. So one part is just this P and Q. That's one small part of it. Another small part of it is this P or Q. And then another small part of it is you incorporate this and. And those are the parts of the proposition. That is how you decompose this proposition into many parts. Does it make sense to people how I've decomposed this? I start from the very small parts, the ones that just consist of two propositions and a connective, so P and Q, P or Q, and then I start building up larger and larger things. So this green box is one connective with another connective attached, so two connectives. And then this blue one, well, that's just an implication, but it happens to consist of one big part, implies one bigger part. All right, so what I do then is I make each one of these their own column. So P and Q will be a column. P or Q will be a column. Not P or Q will be a column. And then the whole thing, P and Q implies not P or Q. That will also be a column. And this is my truth table. I'm finished laying it out at this point. And the critical thing is the thing I'm interested in is this column here. This is where my answer is because it's the whole proposition. It's the entire compound proposition that I was asking about. All right, so now we start to fill in the table, and we have one row for every truth value combination of the propositions P and Q. So what can they be? Well, they can each be either true or false. So there's two possibilities and two propositions I have to fill out. So there should be a total of 4 rows. The way you do that systematically is this. So you start with the leftmost proposition. You fill the first half of the rows as T's, the second half of the rows as F's. And then you move 1 over, and you fill a quarter of the rows as T, a quarter of the rows as F, a quarter of the rows as T, and a quarter of the rows as F. And in this particular case, because there's only 4 rows, a quarter of 4 is 1. So you're really just alternating true and false. Okay? We'll see an example in a little bit where we have 3 variables. And if we have 3 variables, we'll have how many rows? Yeah, we'll have 2 to the power 3, which is 8 rows. All right. So now we have to fill this thing out, but that's not too bad, because now we just need to remember how the connectives work. So here's P and Q in the first one. If P is true and Q is true, then P and Q is true. Otherwise, it's false. So I've successfully filled out that row. That column. Now we move to the next column, P or Q. Well, if P and Q are both true, P or Q is true. If P is true and Q is false, P or Q is true. If P is false and Q is true, then P or Q is true. But if they're both false, then P or Q is false. Okay? So notice what happened. This column here depends on P and Q. This column here depends on P and Q. But now this next column, it only depends on that column. I don't need to go all the way back. So that's kind of nice. What's the negation of P or Q? Well, if P or Q is true, then the negation is false. If it's true, then the negation is false. If it's true, then the negation is false. If it's false, then the negation is true. So I only need to go back and look at that last one. And now to finish the very last column, I say, okay, well, P and Q, I'll do this in a different color so it's not that confusing. P and Q is just this column here, and not P or Q is just that column there. So I want this column implies that column. That's the operation I'm doing in the very last column. So I have true implies false is false. False implies false is true. False implies false is true. And false implies true is true. So this very last column is the answer to the question, really. That's the important part of the truth table. Questions? Yeah. 2 to the power 3. Yeah. So that's going to be for when we have 3 propositions like P, Q, and R. In this example, we only have 2 propositions, P and Q. Other questions? Yeah.
For the last one?
Yeah.
So false implies true becomes true because of the benefit of the doubt?
It becomes, so whenever the hypothesis is false, the implication is true. Yes. Other questions? All right. So we can add more rows, as a couple of people have observed. So let's try doing that. Here's another example. So let's do the truth table for P and Q. I'm going to do a different example. let's do P implies not Q or R. Let's do this as a truth table. Okay, well, we start the same way. There's three propositions here, P, Q, and R. All right, now let's break this proposition down into smaller parts. Not Q is a smaller part. Not Q or R is a smaller part. And P implies not Q or R is another part, and that happens to be the whole thing. So those are the different things we'll need to look at. So we have not Q or R, and then P implies not Q or R. And it's that very last one that we're interested in. Okay, so now we have to fill out this table, and we know that there's 8 rows that we're interested in, right? Because there's 3 propositions, and they could each be true or false. So there's 2 times 2 times 2, which is 2 to the 3, or 8 different combinations we have to consider. And remember, every row is a combination. So the way you fill it out is systematically. If you don't fill it out systematically, 2 things will happen. You'll almost certainly forget one. And on top of that, even if you remember all of them, your truth table will look different from everyone else's, which, while not incorrect, is likely to upset the TA, who now has to go through and check your truth table very, very carefully. So, the way you do it is this. The first column is half true, half false. Okay? The second column is quarter true, quarter false. Quarter true, quarter false. Well, a quarter of 8 is 2, so that's true, false. True, false. The fourth column is an 8th true, an 8th false, an 8th true, an 8th false, and so on. There's 8 rows, so an 8th of 8 is 1. So the last column alternates true and false, and that's actually always the case. So true, false, true, false, true, false, true, false. What you should definitely do when you are doing this is count the number of rows in your truth table. It should be 2 to the number of variables you have. If it's not, you've made a mistake. You've left out a row or added an extra row or something. If you have trouble remembering how to do this, one trick you can do is treat the T's as 1s and the F's as 0s, and you're counting down in binary. That is the exact same thing. That's exactly how you count this. So if you can remember how to do that, then you know how to do this, although I'm not sure that that's simpler. All right, so now we actually want to make this truth table. So not Q, I take what's in the second column and flip it. So false, false, true, true, false, false, true, true. Next column, not Q or R, that's this column or this column. So true or false is true, false or false is false, true or true is true, that's true, true, false, true, true. Not going to go through every one of these. All right, and the very last one is P implies this column. So it's this thing here implies that thing there. So true implies true is true. True implies false is false. True implies true is true. True implies true is true. And at this point, I should notice that I have all F's for the rest of that column, which means the answer is going to be true no matter what. You should always look for shortcuts like that. So this last column is really the truth table, the important part of it for this proposition. So why would we ever do this? Well, if someone now gave us some truth value settings, we could immediately look up the value of the compound proposition without really doing a lot of work. If someone said, John, P is true, Q is false, R is true, I would look right here and say, oh, the expression is true. I wouldn't need to do any extra work. Yeah? So if the hypothesis is false, if the thing on the left is false, then the implication is true no matter what's on the right. All right. So that's one use of truth tables, but it's unlikely someone would stop you in the street and ask you to evaluate a proposition. There's other more important uses of them. Question? It has 2 to the 3 rows, yeah. Yeah, so it does have this kind of recursive structure as well. So if you look, for example, at this quadrant, that's exactly what you'd have in a truth table on 4 variables up here. And then you repeat it again down here. And the reason you repeat it twice is because the other one could be true or false. So it does have this kind of recursive structure. That's another reasonable way of memorizing it. Other questions? All right. So sometimes you'll get interesting cases when you do your truth table. And the interesting case is when the last column, the column that you're interested in, is either all true or all false. So that means it's true regardless of what the true settings are, or false regardless of what the true settings are. So let's talk about this. Sometimes truth value doesn't depend on other truth value or values. The compound proposition is always true or always false. Okay, so as an example, let's do P or not P. Right? This is a truth table for one thing, so it will have 2 to the 1 rows, or 2. So the only variable I'm interested in is P, and P could be either true or false. And if that's the case, then not P is false or true. And P or not P is true or false, which is true, or false or true, which is also true. So notice that no matter what the value of P is, P or not P is true. Right? It doesn't matter what value you give this proposition, it will always give you the value true. That kind of statement is called a tautology. So what that means is it evaluates to true regardless of the true settings of the propositions. The compound proposition is always true. So this example here is always true. Here's an example of something that's always false. If we have the variable P, and we look at P and not P, well, P can be true or false, so not P is false and true. And P and not P in either case is false. Right? There's no way that that proposition can be true regardless of the value of P. Yeah? Yeah, so I use statement to mean a proposition that's bigger than just a single letter, which is a compound proposition. All right, so such a statement, if it's always false, is a contradiction. So always false is this one. Okay? Of course, there's lots of other different types of propositions. There's types where sometimes it's true, sometimes it's false. Those are the other two examples we saw. If a statement isn't a tautology and it's not a contradiction, then truth values do alter the outcome, and we say it's a contingency. So if a statement is neither a tautology nor a contradiction, then it is a contingency. All right, so if I ask you, is something a tautology, is something a contradiction, is something a contingency, the way you answer that, or at least the way we've seen so far, is to make a truth table, look at the last column. If the last column is all true, then it's a tautology. If it's all false, then it's a contradiction. And if it's a mix of true and false, then it's a contingency. So let's do some examples. So here's one. We have A or B and not A or C implies B or C. Okay, so I want to know, is this thing a tautology, contradiction, or contingency? I might ask you to classify it as one of those three things. So all we know how to do to solve this, there are other ways, but all we know so far is to do a truth table for this thing. So let's do that. How many propositions do I have? Well, I have A, B, and C. So I know that I'll need 8 rows. So I set this up, A, B, and C. All right, now let's break this down into smaller parts. We know we'll need an A or B. We'll need a not A. We'll need a not A or C. Oops. We'll need a or B and not A or C. And then we'll need that whole thing implies B or C. I'm going to do something that's a bit of a shortcut. I'm going to call this X. And I'm just going to write X implies B or C. And I'm just doing that to save some space. Right? I'm saying let X be that, and now I'm going to use X as I like. That's a common trick, and I suggest you do that, otherwise your truth tables start to run way off the side of your page. That's okay on a tablet because the page is infinitely long, but yeah. There is a column for B and C, right? Right here. Sorry. I see what you're saying. Yes, you would. Yeah, you'd want B or C, and then you'd want X implies B or C. Yes, you're right. Sorry. All right, so let's start filling this thing out. This is a bit longer. This is the longest truth table we've done so far, and it will be the longest truth table we do. All right, so A can be true, 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 false, 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 false. B can be true, true, false, false, true, true, false, false. And C can be true, false, true, false, true, false, true, false. When you're doing these, please be careful not to do this. It's kind of annoying. It's worth 0 marks, by the way. We caught on to that trick. It's not original. All right, so let's start filling this thing out. A or B, well, I know that A is true for the first 4, so I can automatically just put trues there. And then B is true for the first 2 here, and then they're both false down here. So as you get more and more experience with these things, you'll be able to fill it out faster and faster, which is always nice. Not A, well, I just flip the first column, so I get false, false, whoops, false, 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 true, 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 true. Not A or C, well, I just take this column here or that column there. So true or false is true, false or false is false. True or false is true, false or false is false, and then not A is true for the rest of this, so I can just put trues there. All right, now I take the and of this column here and that column there. So true and true is true. That's false, true, false, true, true, false, false. Right? Okay. Now we do B or C. So B or C is this column or that column. So true or true is true, true or false is true, false or true is true, and false or false is false. And now we're going to get the exact same pattern down here. So we also get T, 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 F. All right, so the very last thing we need to do is X implies B or C, so that's this column implies that column. So true implies true is true, false implies true is true, true implies true is true, false implies false is true, true implies true is true, true implies true is true, false implies true is true, and false implies false is true. So if we look at this last column, we'll notice that no matter what, we always get true. All right, the answer is always true, no matter what we put into this thing. So that means, by looking at the last column, we know that it's a tautology. Any questions about how I did that? This makes sense? All right. So, as an exercise that you can do at home, stick a negation in front of this entire thing and put it in parentheses. Go through this same exercise and show that it's a contradiction. Right? The exact same thing happens, so I'm not going to do an example. You just get all F's in the last column. But if you know how to make a truth table, it doesn't really matter what you end up with. I will show you one small example, and that's this one. That's not A and B if and only if A or B and not A or not B. So this is kind of a complicated one, but it's only on two variables. And if you understand this one, then you understand what's going on, because this has everything. It has negations, ands, ors, and if and only if. And if it has an if and only if, really it has two ifs. All right, so let's build this thing. We have A and B as our variables. And the parts that we want to build up are A and B. We have not A and B, which I'll call X. We have A or B. We have not B. We have A or not B. We have not A or not B. And we have, running out of room here. We have A or B and not A or not B, and I'll call this Y. And then the very last column is X if and only if Y. There. All right, so this is a long truth table, but it's not very tall, so that's kind of nice. All right, so A can be true or false, B can be true or false, and now I just have to start filling this thing out. So A and B is true there and false there. Not A and B will be false there, but true there. A or B will be true up here, false down there. Not B, well, I just flip column 2 to get false, true, false, true. A or not B, well, that's this column or that column. So true, true, false, true. For this next column, not A or not B, I just negate the previous column. So that's easy. False, false, true, false. And now for this column, I look at, what do I look at? I look at this column and A or B, which is this column. Right? That's what goes in there. So true and false is false. True and false is false. True and true is true. False and false is false. And now I look at this column if and only if this column. So false if and only if false is true. True if and only if false is false. And in fact, I can stop right here if all I want to do is decide if it's a contradiction or contingency or tautology. True if and only if true is true, and true if and only if false is false. Okay, so this is what I get here. And notice, unless I've made a mistake, but notice that I get both possible truth values out of it. Right? It could be true or false. So that means it's a contingency. Any questions about that? Yeah?
So you can do all this on a computer using bitwise operations?
Yeah. Yeah. I just sort of did it in, I like to, I mean, you could rearrange the columns for sure. This is just the way that I like to do it. I like to start going left to right as much as I can. Yeah?
For the third last column, the not A or not B.
Yeah?
Can you change the not in the column before that? Does anyone know?
The third, sorry, which column? This one?
Yeah. Would it be like, when you use the column before it? for that?
Yeah, we did. So true goes to false. Yeah. Other questions? All right, so this is how you answer questions about tautology, contradiction, contingency. It's one way to do it. All right? So the next question we might want to ask ourselves goes back to earlier in this lecture when we were doing translations. So that's the question of logical equivalences. So sometimes, as we've already noticed, there's more than one way to write a proposition. In logic, I should say. All right, so as an example, P and not P, that means exactly the same thing, right? If you negate something twice, or do a double negation, then it's the same thing as the original. So we have special notation for this. We write that P is logically equivalent to not P. Okay, so it's like an equal sign, but there's 3 lines instead of 2. So that symbol means logically equal to. So what does it mean for logically equivalent to? What does it mean for 2 propositions to be logically equivalent? What does that mean? Yeah? Yeah, it's going to mean that their truth tables are the same in the sense that the last columns match. Right? They might have different middle columns, but that doesn't really affect anything. That's just for our benefit to make it easier to write it. The important thing is the last column. And what that corresponds to is the fact that no matter what truth settings you pick, if you feed the same ones into both propositions, you'll get the same output. Right? And that's really the only thing that makes sense to think of as causing them to be equivalent. It's the same thing if you had 2 expressions in arithmetic, right? X plus x is equal to 2 times x, because no matter what the value x you choose, they evaluate to the same thing. Right? That's what it means to be equal. Well, that's what it means to be logically equivalent. Okay? All right. So, to tell if two expressions are logically equivalent, we do exactly as you suggest. We make the truth table, check the last column, and see if they're the same. Okay, so we were debating about this thing earlier, so it might be a good idea to settle this debate. So if you'll bear with me, I'll go up and get exactly what the issue was. So this is what we couldn't decide on earlier. So let's try to decide now. Are these two things logically equivalent? Well, let's settle that before we go home. We have three variables, m, I, and d. Okay. And one of the propositions, I'll need I or d, and I'll need m implies I or d. And I'm going to do these truth tables really as one truth table just for convenience. So I have m implies I, m implies d. I guess I don't really need the brackets there yet. And I'll call this x, I'll call this y, and I want x or y. All right. So remember, the columns we're interested in are this column right here and this column right here. So we want to know, are these equal? So let's find out. So m could be true, 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 false, 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 false. I could be true, false, true, false. And d could be true, false, true, false, true, false, true, false. Okay, so I or d is true, 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 false, true, 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 false. And so m implies I or d will be true, 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 false, and then true, 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 true. I know those last four are true because m is false. So we're half done. We know the truth table for one of the two things. Let's figure out the truth table for the other one. M implies I, so true implies true is true. True implies true is true. True implies false is false twice. And then these last ones are all true because m is false. Now we do the same for m implies d. True implies true is true. True implies false is false. True implies true is true. True implies false is false. And now the rest are true. All right. So now we take the or of these two things to get true, 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 true. Yeah, sorry, I figured there must be a mistake there. Yes, right there. So true, 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 false, true, 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 true. So these are the columns we're interested in. And we ask ourselves, are they the same? And the answer is no. Or sorry, no, the answer is yes. Yes, so these are exactly the same. So that must mean that the expressions are saying exactly the same thing. And notice now we don't have to appeal to intuition. We don't need to use words to argue this out. We know for sure that these are exactly the same. We look at the truth tables and the final columns match. So we know for sure that in fact both of those were valid answers to the question I posed earlier in the lecture. They're exactly equivalent. It makes no difference. One of them corresponds more closely to what the sentence says in English, but that doesn't matter, right? All we care about is the logic. So next class, I'm going to teach you about another way to decide if two expressions are logically equivalent, and a consequence of that will be another way to decide if it's a tautology or contradiction. So that's it for tonight. Thanks, guys.